So today, we're unpacking a concept that is, well, literally mind-bending. I want you to go ahead and just forget everything you thought you knew about how temperature works. Usually we think of heat as this chaotic thing, right? Something that just kind of radiates out and does its own thing. Like a hot cup of coffee just loses heat to the room in every single direction. But there's a groundbreaking new study that is completely flipping that script. We're looking at a brand new smart material that lets scientists control heat with an absolute unbelievable level of precision. We're not just talking about insulating things here. We are talking about actively steering thermal energy. So what if we could program heat just like we program data on a microchip? I mean, imagine treating the flow of thermal energy exactly like electricity running through a circuit board. With electricity, right, we use switches, transistors, and wires to tell the current exactly where to go, when to stop, and when to store information. Until now, trying to do that with heat was considered pretty much impossible. But that is exactly what this new scientific breakthrough is making a reality. Okay, to really appreciate this, let's jump into Section 1, the strict rules of heat and the invisible boundaries of thermal energy. See, for decades, scientists have been banging their heads against this giant brick wall, and that wall is known as reciprocity. In the world of physics, reciprocity is a fundamental, totally rigid law. It basically dictates that if a material is really good at absorbing heat from a specific direction and at a specific wavelength, it's actually forced by the laws of physics to emit heat in that exact same way. They are totally locked together. So because of reciprocity, it's historically been impossible to independently control how heat is absorbed and how it's released. You couldn't just tell a material, hey, absorb heat from the left but only release it to the right. Physics simply said, no way, it goes both ways. But shattering that reciprocity link, that is the crucial first step, because doing so unlocks an entirely new class of technologies. By decoupling absorption from emission, engineers can finally steer thermal energy exactly where they want it to go. And this isn't just some fun parlor trick in a lab. It's literally the fundamental starting point toward completely reimagining thermal management, energy conversion, and even highly sensitive infrared sensing. So, who actually pulled off the impossible? Let's get into Section 2, breaking the reciprocity barrier, meet the rule breakers. The sheer brainpower behind this innovation is just remarkable. We are looking at a brilliant international research team spearheaded by scientists in Japan. The whole effort was led by Professor Koichi Okamoto and co-led by Dr. Shunsuke Mirai at Osaka Metropolitan University's Graduate School of Engineering. And to prove just how legitimate and groundbreaking this whole thing is, their successful creation of a device to independently steer thermal energy was actually recently published in the highly prestigious journal Laser and Photonics Reviews. So they didn't just theorize this on a whiteboard, they actually built it. Dr. Mirai's perspective on this is super fascinating. He said, "We made heat radiation behave in a smarter way. Achieving these capabilities in a working model could enable a new generation of efficient infrared emitters, thermal energy devices, sensors, and photonic memory technologies." Now, think about that phrasing for a second. By giving heat a kind of agency, the technology becomes incredibly dynamic. It is no longer passive, it's active. When he mentions enabling a new generation of efficient infrared emitters and photonic memory, he's basically highlighting that a working model of this could literally change the hardware of our future computers. But how did they actually do it? Let's zoom all the way down to the nanoscale in Section 3, how the smart material works, the ingredients of the breakthrough. It is essentially a chemical tag team. First up, we've got magneto-optical materials. And just as the name implies, these are incredibly unique materials that fundamentally change the way they interact with light and heat whenever they're exposed to a magnetic field. But on its own, that's just not enough. The team actually paired that magneto-optical material with a phase change material, specifically a substance known as GST. And when you put these two things together, boom, you create this dynamic system that is suddenly capable of totally ignoring the old rules and controlling the direction of thermal radiation. The mechanism is highly elegant in practice. So step 1, heat gets absorbed by the material from the right side. Easy enough. Step 2, the physical structure itself heats up, holding on to that thermal energy. But then step 3 is where the real magic happens. Instead of just radiating that heat back out in all directions, or back out to the right where it came from, the heat is exclusively radiated to the left side, which ends up cooling the structure down, so it absorbs from one direction and emits in another. They've effectively steered the energy. It's wild. Of course, early iterations always have some flaws. So let's look at Section 4, a leap in design, upgrading the old rules of physics. So earlier designs were honestly incredibly limited. They only worked if light and heat hit them at these very steep, awkward angles, which made them highly inefficient. They were inconsistent, and probably most problematically, the absolute second you turn the power off, they forgot what they were doing. They just lost their programmed state. But this new system, it's the ultimate game changer. It responds correctly even at near normal incidents, meaning it works even when energy hits it almost straight on. It offers highly efficient, totally reliable switching. But here is the real kicker, the absolute best part. It retains its stored programmed state without continuous power. Yep, that zero power memory retention means you do not need a constant flow of electricity to keep the heat programmed. So, what's the actual technological payoff of all this? Let's zoom back out to our world in Section 5, the future of programmable heat, turning temperature into data. To really ground the science here, we have to look at Professor Okamoto's ultimate vision. He says our ultimate goal is to develop compact devices that can actively control heat radiation, much like electronic circuits control the flow of electricity. And there is that core analogy again. Look, we've spent the last 100 years mastering the electron. We literally built the entire modern world, computers, smartphones, the internet, just by learning to manipulate electrical charges. Professor Okamoto is pointing toward a future where we do the exact same thing with the exact same level of precision, but using heat. If they actually achieve that goal, we are looking at the dawn of the era of photonic memory. This means vastly smarter, incredibly precise infrared sensors. We're looking at highly efficient energy conversion systems that don't just waste thermal energy, but actively harness and direct it. It opens the door for completely advanced thermal communication devices. But honestly, the most mind-blowing application here is the photonic memory itself. Imagine a computer memory system that stores information, the actual zeros and ones of data, using light and heat instead of electrical charges. It would be faster, far more energy efficient, and just fundamentally different from anything we use today. Which leaves us with a pretty massive question. When data is stored using light and heat, what will the computers of tomorrow actually look like? I mean, if we don't have to rely on traditional electronics and these loud, power-hungry cooling fans, if the heat itself is literally part of the programming, the possibilities are virtually endless. We are standing right on the edge of a completely new frontier in physics and computing.